So my name is Sandeep Yadav. I'm a Prime Minister's Research Fellow at IIT Bombay. I'm pursuing my PhD in Energy Science and Engineering Department at IIT Bombay, and I'm a fourth year PhD student. I'm gonna I'm a PMRF TA in this course, so I will be taking a weekly live sessions on these topics, like whatever the sir teaches in the classes. So I will take the your problems related to the content and the numerical problems basically. So that will help you grasp more and more about this course. Now you can hear me, and as well as you can see my screen and see my video. Yeah, thanks. So before starting my lecture, on the tutorials and the numericals. I will directly not go on the numericals because I just wanted to give you a brief about what has happened in the past 1 week, whatever the lecture that you have attended. So I'll just give you a brief summary about the all the 6 lectures, and then I will start with the numericals. I think someone has unmuted. Okay. Anik Pal, can you unmute yourself so that I
Okay.
can start? Yeah. So in the so let me start. So in the first lecture, sir started with the energy. We have discussed about the energy flow diagrams that includes the how the energy flow, like from the primary energy to the end user activities, how energy flows throughout the energy systems, like primary energy converter to the energy conversion facility, and to secondary energy that's called like from the coal, oil, or solar, we generate electricity. So that's a conversion from the primary to the secondary energy sources, and it is transmitted to us, transmitted to the final energy, so that it can be consumed. So that is being consumed by the transmission and the distribution systems, and the final energy will be going into the energy utilization equipment like automotive, lamp, or solar, whatever the use of that electricity or the transported form of energy. And then we will get some useful energy, and finally we will use the end user activity. That can be a illumination, that electricity can be used in the illumination or any other thing that we wanted to use. And then yeah, we have seen the end use energy service and the device. So whatever there's a difference between the end use and the energy service. Like if you see cooking is a end use of energy, and food cooked is the energy service. Same as the lighting. Lighting is the end use, and the illumination is the energy service from that. So this table shows that all kind of energy and the end users services. Moving ahead. So this is a great example of how the energy flow happens into the energy system. Like coal is being converted to the from is mined from some efficiency, and then it's transported to the power plant, and then power, from the electricity generated from the power plant is distributed, and the electricity to the farmer, and then it is converted to the motor, and then finally the efficiency of the pump and the final output. So you can see that all the electricity, if you want, what is the final energy in the uh, pump output we get. So we just need to multiply all the efficiency to get the final energy output. So that would be very less. So that's how show the what at what stages the energy is getting lost. Now, these are the terms like primary energy, secondary energy. These are already explained in the detail. I will just go through the briefly. And these are the conventional units like joule, calorie, British thermal units, quart, kilowatt hour. These are the units of that energy. Different kinds of application requires a different kinds of units. So that these are all the units that are being used in the. So this is the this is the question that's solved in the uh, class. So, and if you see that graph, that is from the 10 raised to power 1 joule, that is going to the 10 raised to power 21. Yeah, 10 is equal to 21, and that is the highest form of that unit that's called zeta joule. Now, what is the total amount of primary energy used by the world? So this is the global energy use. Sir explained that this is the resources that you must have gone through that, and the history of the world primary energy use from the steam engines. We have now we are going in the age of internet. So this is the all the transformation that has happened throughout the years. And this is the global energy flows, how the energy is converted from the primary, secondary, final, the useful, and what is the wastage of that energy. And this is the example of that global energy flow. Now, coming to the global energy flow, there's a detailed example how what fraction of the energy flows is taken out from the different kind of fuels like crude oil, coal, natural gas, new renewables. So that's the global energy use of the world. Now, taking a part of that World Energy Outlook, that's 2016, and that's a projection for the 2040. So if you will see, the gas is will almost like increase in the slightly, but the use of oil will be decreasing, and the other renewables and bioenergy and then nuclear will increase in that. That's assumption as that are made by the World Energy Outlook in the 2017. Moving ahead, what is the energy use of a region depends on that depends on the country, state, and the city. The parameter affecting that that this is the so depend what are the energy used depend on that depend on the population of of the country or a city. So that's a question that's solved in that class. So that's giving a brief about the trend of the world population versus the time for the last 2000 years would be. That would be exponential growth. As you can see in that graph, that graph shows the typical that exponential graph, and the other graphs are similarly compared to that. And this is also showing the like if you see the what the other than the population, what are the other factors that is affecting the global energy use. So these are all the graphs that are like water use, total real GDP, fertilizer consumption, even the McDonald's restaurants and the international tourism are growing exponentially. And the world energy trend that in that so as explained that a trend of world energy use for the last 2000 years will be show that exponential growth with a growth higher than the population because we are using more and more energy. We are using different kind of appliances. New appliances are coming on. So that's why we are moving and the higher than the exponential growth. And coming to the energy outlook of India, that's already explained. The theory part, so I will just cover up all the units, that is physical quantities. What are the units for used for the coal, that is tons? What are the units used for the oil, that is standard units, the barrels? And natural gas, we often use meter cube, and normal meter cube, standard meter cube. Electricity, we use generally kilowatt hour. That's a one unit we usually call it. And the GCV, or we can say a gross calorific value, coal equivalent, and that's used for the coal and oil. Like if you want to convert that natural gas, we can just convert it to the equivalent coal or the oil equivalent. Now, there are some terms that we are going to use in the numericals. That is a plant load factor. That is the uh, that formula shows that actual generation of the power plant. That suppose there's a power plant of 660 megawatt, and that will be the actual. And we want to get the plant load factor from that. So if we see the actual generation of the power plant divided by the maximum generation if operated continuously. Suppose we have a capacity of 660, but we can generate only of 440 megawatt. So that will be approximately a generation of like 70 to 80% plant load factor. Similarly, auxiliary consumption. Auxiliary consumption is the power consumed within the plant itself, like in the operation of pumps or some other staff, whether the staffs and the other utilities of the plant. That's called the auxiliary consumption. So that's the power consumed within the plant itself. The gross power output, that the auxiliary consumption, net power output will be the gross power output and subtracted by the auxiliary consumption. And the auxiliary consumption percentage will be, we can calculate for the auxiliary consumption by net power output into 100. So that will give us, so these are the things that will be used to help you to solve the numerical problems. Now, this example cell is already explained, so I will not go through that. Now, this is a great pathways of the for the end users. So, if you want to see the any kind of energy like solar, biomass, wind, small hydro, geothermal, and they are generating most of them are generating the electricity, and we want to use the different applications like space cooling, space heating, water, cooking, lighting, and what are the end use of energy that we are getting. This graph shows the, all of them simultaneously. Now, moving ahead to the lecture 2, 3, and 4. So any of you having any doubt, I can just clear it here. Otherwise, I will go to the numerical problems. You can just comment or unmute yourself and just ask if you have any doubt. So let me just start with giving you a summary of the lecture 2. Yeah. So lecture 2 explains the same thing. Like this is the same thing that like issues. Why is the environment important? That's basically lecture 2 shows the energy and the environment relations. So starting with the human like interaction between the energy system with the environment. So we can see that energy, that's exploration, production, conversion, and the utilization. And this depends on the various factors like human natural sources, ionizing radiation, aesthetics, waste heat, sound, electromagnetic radiation, solid and liquid gases, effluents. This is the relation to the energy and the environment. So this will affect like solid from the any of the energy system. There will be some outputs like if you see the power plant or the fertilizer plants, there will be some solid or liquid or gaseous effluent that will affect the environment. And from the environment, we will see the human and the natural resources that we are consuming. Similarly, there will be some waste heat that will be exhausted, being exhausted in the environment that will affect the environment. So this slide shows the interaction between the energy systems with the environment. Now, moving ahead to the energy consumption and the air pollution, these are the different pollutants that are being explained, like sulfur dioxide, NOx, that's a combination of NO plus NO2, carbon monoxide, SPMs, CO2, and the CFCs. So there will be some adverse health impacts that are being explained, like uh, local and the human. So major of that is called the human disruption index. So what is human disruption? This I'm going into detail because we are going to use that in the uh, numericals. To if you want to find that what is the human disruption index, that is the ratio of human generated flow of a given pollutant to the natural baseline flow. That means suppose there is a some amount of CO2 that is being generated by us, it can be recovered by the environment itself without doing any environmental measure. So that is the baseline of that flow. But we are far away from that. We are generating more and more CO2 and the other pollutants that are being not. The environment is not able to cope up with the pollutant that we are getting generated. So that is the human disruption index. That what is the disruption that we are causing to the environment. So I hope so. If you can see that DI, there's a disruption index for the different kind of pollutants like lead emissions, oil to oceans, cadmium, methane. So these are the if you see the any of the disruption index is not less than one. So we are generating more and more emission that environment can handle it. So this is the other than that nitrogen fixation, NOx, and the carbon dioxides. So we are getting the more and more hum, human being like environment being disrupted by the humans. Now going ahead with the So these are all the theory parts that are excellently explained. I will not go through it. Now examine the trend of CO2 shown here. Which of the following is true? CO2 concentration shows an overall increase over the several years, but fluctuate randomly within the years. So, and the seasonal fluctuation in the CO2 concentration is due to the seasonal fluctuation in the energy pattern. The seasonal fluctuation is due to the local in the Hawaii. The seasonal fluctuations are due to the melting in the summer. So we'll see that this question is being already solved, but I will just giving you a brief that we can see that CO2 concentration is being several else, but it fluctuates randomly within the years, but it's constantly increasing in the years, as we can see. Now, in the global warming potential, that's a very, very important phenomena. We generally use it. What is the GWP in short? We say what is the GWP of any pollutant. Generally, we use it for the refrigerant or because in the refrigerant industry or the air conditioning, it's commonly used. What is the GWP of that refrigerant? So in that case, we are just like CO2 considering a lifetime of 100 years. We are considering CO2 as a baseline. So global warming potential is compared with the GWP of CO2 as a one. So if we see global warming potential of for 100 years, the CO2 is one. So compared to the CO2, CH4 is having 10 times more global warming potential, and 2 is having 120 times more global warming potential. Sorry, potential. And if you see for the like CFCs, SCFCs, and SFs, these are the general uh, refrigerant. They're having a far more than one as compared to the CO2 global warming potential. Now, moving ahead. So one daily, this is the disability adjusted lost year. So one DALY can be thought of a one lost year of healthy life. So the sum of these DALYs across the population or the burden of diseases can be thought as a measurement of the gap between the current health years status of an ideal health situation where the entire population lives to an advanced age free of disease and disability. So that is the source taken from the WHO. So that's already being explained. I'm just giving everybody the disability adjusted lost years in the. So now we have to calculate the Kaya identity. Kaya identity is the very important terms as we compare the energy systems to the environment. So that is the total CO2 emissions. The total CO2 emissions can be divided by the CO2 emissions by the carbon intensity. As we see, the first part is being covered by the CO2 intensity. That's carbon intensity. Second is the E by GDP, that is energy intensity of the economy. And other than the GDP by the population, and finally, we will see the total CO2 emissions will be comes out to be on some unit that we use in the numericals. So that's how we will use the Kaya identity. Suppose you are giving the carbon, you have given the carbon intensity and the energy intensity. You have to calculate the total CO2 emissions. So you can use that formula to calculate that Kaya identity. So these are all the theory part. Other than that, the other important factors are being covered. That is the emission factor. So emission per unit of the output. Suppose we are generating 1 kilowatt of the power, and how much emissions that we are generating, like CO2 emissions we are generating from the power plant. That is the emission factor. It depends on the consumption of a fuel, efficiency, characteristics of the conversion device can all be done for all the pollutants. But we are majorly use terms in the for the CO2s. So that examples are already solved. Now the options for the low carbon economy or low carbon options are there that we can have the mitigation option. We can increase the sinks. We can reduce the sources like afforestation and fuel mixes and energy efficiency. And we can use the renewable nuclear and the carbon sequestration and like CCS, carbon capture and the sequestration, and some other adaptation techniques can be used for the option for the low carbon. So that's all for the summary. I'm just have extra 5 minutes to have any doubts if you have. Other than I will start with the numerical questions. I think 10 people are joined. If you have any questions, please let me know. You can comment down your queries before we start. Okay, just give me a minute. So I don't think so that you're going to ask me a question now, but I will ask you some questions in between. Let me just check if I'm able to still the classes. Yeah. So let's start with the numerical questions that we have. We'll start with the some short questions in between. Yeah. So now, starting from the first question, can anybody confirm that I'm still visible? Yeah. Let me just confirm it by myself. Yeah. And I'm audible too. Yeah. Yeah. So going from the starting from the first question, consider that the energy from a hydro power plant starting with water in a reservoir is eventually utilized to provide cooling from a fan in a household. Identify the form of secondary energy and the useful energy respectively. So this question is asking from attempting a hydro power plant. We're using it for generating electricity, and final end user is, as you can see here, finally end users is being starting from the hydro reservoir, and end user is and energy as a service we are getting as a cooling. So now it is being asked from the hydro. It is being asked that to provide the cooling from a fan household, identify the form of secondary energy and the useful energy. So if we'll see, this is the hydro reservoir is the form of a primary energy. Okay. Hydro power plant is the energy conversion system. So now, what will hydro power plant generate? Can anyone of you comment on that? I'm just opening the comment section. You can just comment down your answers. I just want to interact, so that will be more useful for you to. Yeah. So power. Some of you have commented the power. So let me just open the chat box. So what we can write power in terms of electricity. So we can just write it like electricity. Great. Yeah. Yeah. So how? So that's very clear from your comments also. Hydro power plant will generate electricity. So now we can write it here, electricity. I'm going very slow because I just don't wanted to rush and match the level of all the students. So identify the form of a secondary energy. So here electricity is being a secondary energy. Now electricity is being having transmission and the distribution of energy, then it will be again electricity. It will be finally goes to a fan that's as being called in the question, and fan will provide us what can be the gap between the fan and the cooling. That will be like kinetic energy. So that is called a useful energy. That is a form of useful energy. So now suppose we will add some efficiencies in between. Like if you will say the efficiency of a hydropower plant is 55%. Sorry, like so we will add efficiency 55%, transmission and the losses we add 15%, and fan efficiency we will add at as a 80%. And so what will be the final amount of energy we are getting here if you are generating a 500 megawatt in that sorry, suppose we are having a hydro reservoir of five we are having a hydro power plant of sorry, we are having a hydro reservoir of 500 megawatts. So how much energy we are getting at a energy service? So it's very simple. We can just multiply all the efficiencies. Like if you will see having a 500 megawatt initially, hydropower plant is generating electricity at 55%, and transmission and the distribution losses. So these are the losses of 15%. So we can't multiply here the losses. We have to just divide by subtract from the one. So that will be 85% energy will be transported. So if you multiply by 15, then the overall efficiency of the whole system will be less than 15%. So we have to be careful about what we are multiplying. Now, fan is having efficiency of 80%. Finally, so what is the amount of energy that we're getting? Like 0.55 into 0.85 into 0.80 multiplied by 500. So we are getting only 187 megawatt of electricity uh, uh, as a cooling service. So that's how that's how this question is explained. So we have solved two questions in the one. We will solve one more question like this. And the same question like the question number two. Well, question number two, the human disruption index. An index computing the losses in the GDP. So what is the human disruption index? So let me just go through the comments. Electricity and kinetic energy, multiplication of, yeah, Rachit, you're right. The multiplication of all the electricity, all the efficiencies, but we have to be careful about the. Okay, okay. So please repeat the second part. So I'm repeating the second part of the question again. So please bear with me because some of the I think missed it. So here, if you will see, suppose we have a 500 megawatt of hydro reservoir, and we are having a hydro power plant having efficiency of 55%, and transmission losses we are having 15%. So efficiency will be 1 minus 15%, correct? And the fan is having efficiency of 80%. So finally, how much energy we are getting at last? That will be just a multiplication in the 500 megawatt multiplied by 0.55 into 1 minus 0.15 into 0.80, and that will be briefly comes out to be 187 megawatt. So I hope it's clear, Binay.
Yes, sir.
Yeah. Now moving to the question number 2, what is the human disruption index is? So human disruption, so here are the options. I've already explained this in the class. An index computing the losses in the loss in the GDP due to the disruption in the environment. No, we didn't uh, added any economic impact in the human disruption. A measure of the gap between the current health status and the ideal health situation for every 10,000 persons. No. The ratio of human generated flow of a pollutant to its natural flow. Yes. And the uh, a measure of a number of lost years of a healthy human life due to the environmental pollution. And the final one is a measure of impact of human habitation due to the natural extraction. So I think C, D, and E looks familiar, but option number C is the correct option. If you want to the details, you can just go through the uh, lecture once again. Even this tutorials that I'm solving the question, this videos will all also be available in the YouTube. So I will share the link with all the NPTEL team will share the link with you, all of you, so that you can go through these lectures again if you have any doubt. Now moving ahead. Question number 3. Which of the following are not environmental impacts of energy systems? Respiratory health impact, sound pollution, nuclear radiation, changes in disease vectors, auxiliary consumption in the power plants. So here we are asking, like, if you will see respiratory health impact, yes, it is the. So here it is asking the not the environmental impacts. So respiratory health having the impact of the to the environment, yes. Sound pollution is having the impact, yes. Nuclear radiation is having the impact, yes. Change. So these are the questions that will have a multiple answers. So there's not compulsory that we can use only A or only B. We can use A, B, C as well. So changes in the disease vectors, and finally the auxiliary consumption in the power plant. So that will not have any impact, environmental impact, but because it is the power being generated and used in the power plant itself. So finally the correct answer will be E. So now that's a very easy question that already been spent. Question number 4. Hydrogen is a primary energy source. That fact is true or false? So I just wanted to just answer in the comment boxes. Yes, please go ahead. Hydrogen is a primary energy source. False. Can you please explain me why you're calling it as a false? Yeah, hydrogen is a primary energy source. No, that's not true. Hydrogen is not freely available in the environment. We can't use it directly. It is available in the not in the concentrated form. It's diluted, so we can't use that in from the environment. So that's why it's not a primary energy. So if you want to use from the hydrogen, we can generate from the electrolysis or from the any other product. So that's a secondary form of energy. That's not a primary source of energy. That's why that statement is false. Moving ahead. Question number. If you have any doubts, you can still ask. We are just 4 questions. Okay. Now moving ahead to the fifth question, that is the energy intensity of an economy can be reduced by. So that's a multiple option question. So you can just answer the what are the options that is being correct in that. Like energy intensity of an economy can be reduced by shifting of energy based economy. Is it? Is the shifting of shifting to a service based economy? We can reduce the energy intensity. Yes, we can reduce it. So shifting to a manufacturing based economy. No, we can't decrease the energy intensity by shifting to a manufacturing based economy. Decreasing the GDP. Yes, we will decrease the GDP. Sorry, if you will decrease the GDP, we can increase the intensity. No, increase the GDP will increase the intensity. Yes. So now, like final, the demand side management to improve the efficiency. Efficiency will always improve the things.
Economy.
So the correct option will be
A, D,
A
C.
and E. Correct. So now that's a very related question. Every one of you can answer that. Question number 6. Increase in GDP increases the energy intensity of an economy. We've already solved previously. Increase in GDP increases the energy intensity. So if you will see, let me explain. Energy intensity of
Increase in GDP increases the energy intensity of economy.
economy will be, yes, you're right, but the correct answer will be false. Let me just explain it.
Increase in
Okay, let me
GDP
just
increases the energy intensity of an economy.
so will explain how it is happening. So you can just unmute yourself and just I will just explain it, and we can just have a hear it out. Uh, uh, Prabalika, can you please unmute yourself so that I can explain? Thank you.
Hello, sir.
Yeah,
Uh,
yes, who's this?
I'm Pravalika.
Yeah, please
Like,
go ahead.
should I answer this or?
Yes, you can ask.
I feel it's not always.
Yeah,
It's not always directly linked to increase in the GDP. It can be sustained and then efficiency could be developed.
yeah, there are exceptions, but if you want to go more in the details, so I already explained how the increase in GDP increases the energy intensity. So increase in GDP primarily increases the consumption of the more the energy resources. So suppose if the country's GDP is being increased, so their lifestyle is also getting increased. So we are using more and more appliances and more energy to getting a luxurious life rather than the basic life. So in that sense, if we will see generally GDP increases the energy intensity. So generally it is uh, not true. So I will just explain how it is related. So energy intensity of economy is related by the energy intensity of economy, primary energy consumption divided by GDP. So suppose if you will see here GDP. So what we are saying, GDP is increasing. GDP is increasing. So energy intensity of a economy will decrease. So here we are according to increases. So that statement is false. So we are just asking the opposite question, but whatever you're saying is right. You just see what that question is being asked. I hope this answers your question. Thank you. So I'm just moving ahead. Okay. Question number 7, and that's which of the following are not environmental impacts to the energy systems? First is alteration of Earth radiation balance. So here also you have to be careful what is being asked. Which of the following are not environmental impacts? Alteration of Alteration in the Earth's radiation balance. Does it affect the environment? Yes, it will affect. Acid rain, it will severely affect. Photochemical smoke, yes, it's affecting. If you can see the example of Delhi, and if you will see uh, solar energy reaching to the earth, so that's being constant throughout the years. That's something that is very constant. So that's does not having some environmental impact. So that is correct answer for that. Anyone having any doubt in that? I hope not so. So let's move ahead to the last short questions we have. So CO2 has the highest, so you can just consider this CO2 written as this CO2. CO2 has the highest global warming potential among all the greenhouse gases. That's a very tricky question sometimes. Is it true? So Binay is telling it's false. Anyone of any other than him want to answer that question? False. So yes, that statement is false. CO2 has the highest global warming potential. No, we have already CO2 is a baseline that we can compare. As we have seen, global warming potential, that is GWP. That's for the CO2. It is 1. So that's a baseline for the CO2 like global warming potential. Where that's not the highest. So that statement is false. Now, so I will just hold for a minute I will before starting the numerical questions. If you any one of you having any doubt, we have multiple more questions in the theory part, but just I just wanted to give a brief how this will help you to solve the questions in the quiz. These are all the mostly of them are the previous year questions, and similar kind of questions will be asked in the quiz, as you can see. That will help you score more and more marks in the quizzes. Just give me. Now let's start numerical questions. I don't see any comment. So a hydropower plant having a rating of 520 megawatt has an actual energy generation of 3416 gigawatt hour. Calculate the plant load factor in percentage and give the whole number with a decimal point. So see here, it is given that rated output of a plant is 520 megawatt, and the maximum. So if you will see what is the maximum possible generation annually. Would be 520 multiplied by 24 hours into 365 days. So we are considering it as a working as a 24 hours and the 365 days throughout the year. So if you will see multiply all these things, that will comes around. So that's having a unit of megawatt. So we want to just convert into the megawatt hour or some gigawatt hour. So that unit is watt hour. What will be that unit? As we will see that will be around 4,500. And even if you calculate, let me just 520 into 24 into 365. That briefly comes about 455.2 gigawatt hour. So that will be gigawatt hour. So it will be 4 lakh 55 45 lakhs 55,000 200 megawatt hour, but we want to have a higher unit, that's a gigawatt hour. So that will be 455. So that's a simple unit conversion, as you can see. Now, what is plant load factor? That's PLF. PLF is actual generation divided by rated generation. So that is being, so actual generation, it's given in the question 3416 gigawatt hour divided by, if you will just divide it by what is the other thing that we got, 0.2 gigawatt hour. So the gigawatt hour will cancel out and the plant load factor will be a fraction. So if you will significantly convert 3416 divided by 455 into, it typically comes out to be 74.99. So that's, we can just convert it to the 75%. Yeah. And any doubts in this question? Just a very beginner level question. What's the plant load factor? All the things are given. We are just converted the, we have just added this maximum possible generation, and we have just calculated this rated generation, and we have just calculated the plant load factor in that. If you want any comments, you can just unmute yourself and we can talk, and otherwise you can just comment your query. So let's move ahead. That's the other thing is a thermal power plant has an efficiency of 40%. Sorry. Have an efficiency of 40%. Taking a NCV. NCV here is normal calorific value of coal to be 4,500 kilocalorie per kg of coal. Now we have to calculate the coal used per kilowatt hour. So that type of question is very tricky that can be asked in the final exams or some quizzes also. That's so if you will see how to solve it. So let's say if you will see here, what are the things given? Having an efficiency of the power plant is 40%. So we must know what is the output energy, and here the other than NCV of the coal is given 4,500 kilocalorie per kg. So from that we can calculate the output energy. What will be the output energy? 1 kilowatt hour is equal to 3600 kilojoule. That's just a unit conversion, nothing more than that. Therefore, input energy will be output energy. That's a standard formula of efficiency we are using here. Output energy by efficiency. So generally it is efficiency is input upon output. So we are just using that formula here to get. So what is the input energy? 3600. So output energy is 3600 kilowatt hour. Efficiency is given 0.4. So we want to calculate the input energy. Input energy will becomes out to be 3600 divided by 0.4. So that will be 9000 kilojoule. So that's how we calculated the input energy. Now we want to calculate the coal used per kilowatt hour. That will be input energy divided by calorific value, or we can briefly write NCV. NCV will be, so input energy we have just calculated 9000 kilojoule divided by 4500, it's given kilocalorie. If you want to convert that into the same unit like kilojoule, so kilocalories can be converted into the kilojoule by 1 kilocalorie per kg can be converted by 4.18 kilojoule per kg. So that's a conversion factor. We just want to multiply 4.18. So that helps in the kilojoule per kg. So now that thing kilojoule will cancel out. It's cancelled out. Now the final thing we will remain to us will be, so if you will see that 9000 divided by 4500 into 4.18 would be 18,810. So finally it comes out to be, we will divide it briefly, 0.478 kg per kilowatt hour. So if you are seeing here, we are writing from the beginning, we have written kilowatt hour we are using. So the final answer will
Is
be,
it per kilowatt or per kilowatt hour?
it's per kilowatt hour. So anyone having any doubt in this question? So this type of questions are being asked from the whatever the output of the codes. So you should be able to answer these questions. So these are very general life questions. Suppose you have a suppose you're operating a 1000 uh, kilowatt of AC. So you just want to how much coal you are burning in the power plant to use that AC. So you can just calculate it from this, and that we can just use that formula initially that we have solved. You want to see this life. So if you're using coal, so you must already all the things are already available in the internet. The how much what is the efficiency of the coal power plant? What is the transmission and the distribution losses? What is the efficiency of your AC? So in that sense, you can calculate what is the rated power of that air conditioner, how much coal is being burnt at the coal power plant to run the AC for 1 day. So that's a very insightful thing that you can do from this courses. I think you don't have any doubts, so just move ahead. So now moving ahead, a thermal power plant, in the same question. That is for the thermal power plant. So instead of the thermal power plant having efficiency of 40% and the density of the coal is 45, calculate the emission factor in the percentage of like if you want to calculate the emission factor for that, in addition to that, what is the amount of calculate the coal is being used. In addition to we want to calculate in the emission factor in the percentage of the carbon content in the coal is 50%. So now let's do this. So now we have already got that amount of coal per kilowatt hour we are using it 0.478. That's the thing we got. Yes, 478. Now if the carbon content per kilowatt hour will be 0.5, so that 0.5, then we can calculate that the amount of coal is being used will be 0.5 into 0.23, 0.5 into 0.478. That will give us a 0.239 of kg of coal, as the carbon content is 50%. So amount of coal used, amount of actual coal used is this one. Now, if you want to, we know carbon burns in the power plant C plus O2. We are just taking a very simple equation that C plus in the presence of oxygen and just generate the CO2. That's how CO2 is being generated in the power plant. So we know carbon having a mole 22, 12 mole of carbon and 44 moles of CO2 is being generated. So therefore 0.239 kg of carbon can generate 44 divided by 12 into, that's for 1 kg. So we have 0.239 kg. So that will be approximately 0.876 kg of CO2 is being emitted per kilowatt hour. So that's an emission factor. Sorry. So that should be amount of carbon emission instead of amount of amount of carbon emissions. That amount of carbon. coal used. So that will be 0.23 kg of coal. That's the amount of coal used, actual amount of coal used. And then finally, if you were to 0. So these are the things. If you have any doubt in that, I can just still answer. This is one advanced level question than the previous one. So we are just increasing the difficulty
Repeat it.
increasingly. Yeah, please go ahead.
Can you repeat it once again?
Yeah, sure. So I'm just repeating both the questions. So the thermal power plant is having efficiency of 40%, taking an NCV of the coal is 4,500. So first of all, we must know what is the input energy that we have given. So the coal used per kilowatt hour will be input and that is the output energy. So coal used per kilowatt will be the input energy by the NCV. So NCV is given input energy. Sorry, starting from this. Yeah, having efficiency 40%, and the NCP is 45 kilocalorie per kg. So we just need how much output energy is there. So 1 kilowatt hour will be 3600 kilojoule. So therefore, if you want to calculate what is the input energy given, so output energy by efficiency, because efficiency is input upon output. So input we have already output we have given like 3600 kilojoule. Efficiency we have given. So in that sense, we can calculate the input energy, that is 3600 divided by 0.4, that comes out to be this one. Now we want to calculate how much the coal is being used per kilowatt hour. That will be input energy by calorific value. Input energy we have just calculated 9,000 and calorific value is given 4,500. But that is given in the unit of kilocalorie per kg. So we want to convert that into the kilojoule per kg. That's a conversion factor. So that kilojoule will cancel out, and finally thing will go up, and this we will get 0.478 kg of coal being used to generate 1 kilowatt hour of electricity. I hope this question is clear. Now we have moved to the amount of coal
Hello, sir.
being used. Yeah,
Good evening, sir. Am I audible?
yeah, you're audible. Please go ahead.
Arnav this side, sir. Sir, I just typed it as because in the lecture, sir mentioned that the part you mentioned, amount of actual coal used, it is mentioned in the lecture that amount of carbon emission per kWh in the lecture. That's create confusion. That's why I typed it and I'm asking you.
Okay.
As there,
Well,
it is given the carbon content in the coal is 50%. So in the lecture, there are a question it is solved in the by sir also. So
okay.
coal used per kWh, which we got 0.478, and multiplying it's the 50% efficiency. Then we got the amount that carbon emission in the environment. So that's why I'm asking you.
I think you're
50.
yeah. So let me answer. So I think if you will see, you will see the amount of carbon content in the coal, it's just a factor. It does not have any unit. So if you want multiply this thing to this one, so we'll still get a thing like what is the coal is being used per, that is, if you will see, that's kg per kilowatt hour. That's a kg per kilowatt hour. So here also it will be kg per kilowatt hour. Okay, because this thing does not have any that's it unitless.
Yes,
So
yes,
still
that I understand,
that,
sir.
yeah, yeah.
Uh, so both it is same amount of carbon emission or amount of actually coal used is both are same now.
No, that's not a thing. Carbon emission, the amount of CO2 being released to the environment, that's I have calculated in the advanced level, this one. So amount
No,
of
I'm not
carbon
saying
used.
that carbon dioxide, only carbon emission. Then this carbon is
Yeah. Then you're
giving.
right. Then you're right. Exactly.
Yes, I'm only saying that kg of carbon. Then it has
Yeah.
to interact with CO2 and formulate O2 and formulate CO2.
Yeah. Correct. Now I got your question. Thanks.
Okay, sir.
Okay. So that's how we calculate the amount of carbon being used is this one. That's also, and amount of CO2 that is being released in the environment. So we have to do this from the stoichiometric conversion. Stoichiometric conversion. Okay. Stoichiometric calculations. That thing we have done, and we have calculated the emission factor. The emission factor that we have calculated from this, from the taking the mole fractions of the C and oxides of carbon CO2 that is being 44. So finally, we have calculated the emission factor, and this similar type of questions you can solve for the your more practice in that, so that we can get in the previous year questions also. You can see that course that is being floated in the every year, so you can get a different type of questions you can solve for the practice, and you can give the quizzes and the score some good mark. Now moving ahead, and this is I think the final questions. So I think you can unmute yourself, please. Anik,
Yes, sir.
can you please unmute yourself? Oh, sorry, mute yourself. If you don't have any, yeah, thanks. Now, just give me a minute. That question is related to the Kaya identity. Now, what it says, so these are the combined questions. Consider the table given below and answer the question number 5 and 6. Let's see. There are two countries, country A and country B, that's having a different population, like 700 million peoples and 350 million peoples. And its primary energy consumption in exajoules is 80 and 40. G the GDP per is trillion USD. That's 15 and 20. And the total CO2 emissions that is being generated is 2150. So now, which of this country has the higher carbon intensity? Can any one of you?
B.
How you have calculated? The answer is right. So that's
Primary energy divided by GDP.
correct. So let me just solve it for you. Carbon intensity
What is GDP?
is
What is the meaning of triple P in GDP?
triple P is purchasing power parity. How much you can like purchasing power parity of different countries are uh, different. Suppose you are
That
having
is
a
kind.
1 lakh rupees in India and 1 lakh rupees in the
Yeah.
US. So you can't buy the same things. So these are generated in that senses. PPP.
But that is a independent term. No, it is not used in conjunction with the GDP.
No, it's always used in the GDP. You can just see in the, if you want to more details in that, you can just go through with that lectures also again. Just explain you. I have some refer to the notes. Yeah, PPP here refers to the purchasing power parity. Suppose you have 1 lakh rupees and sorry, you have 100 rupees. Suppose you have 100 rupees and you want to buy a burger from the McDonald's. So the same burger that you get in India from the 100 rupees, you can't get that in US, because the US purchasing power parity is lower. You can't get much things in the 100 rupees as you get in India. So that's why to normalize the GDP of all the countries, generally PPP is taken into the account to compare and to calculate the carbon intensity and some environmental terms. I hope this solves your question. So now let's see carbon intensity. Carbon intensity is CO2 emissions divided by primary energy. So what is the CO2 emissions of country 1? 2000. So let's solve for the country 1, A. 2000 divided by primary energy, that is 80. So that comes out to be 25 metric ton plus million tons per hexajoule. Here I'm using MT for the million tons. And for the country B, that is 1500 divided by 40. That will be 37.5 metric ton plus hexajoule. So if you will see here, 37, the higher carbon intensity will be for the country 2. Similarly, if you want to see the energy intensity of an economy for the, I hope you can hear me, economy for the country B. What will be it? So
Two.
we'll see. Can any one of you unmute yourself and yeah, thanks. Thanks, Arthur. Energy intensity. So my name is intensity of an economic country B. Country B. Energy intensity will be
2, sir. A
2
option.
exajoule plus per trillion dollar. I think I don't need to solve that. It's a simple calculation. You can just do that. So the correct answer is 2 exajoule per trillion dollar of USD. For the country B, we are asking. So that will be 40 divided by 20. That's simply the unit. You can just solve this from the unit itself. That's the energy intensity. So if you have any doubt, I can still solve. Otherwise, I will move. Don't know the unit conversions. So these are the unit conversions. Like kilo is generally used for the 10 to the power 3 or 1000. Mega is 10 to the power 6. Giga is 10 to the power 9. Tera is 10. These are the unit conversions that I've used. Like similarly, we will see here, we have used 1 kilowatt hour for 4.18 kilojoules. 1 watt hour is 3.6 kilojoules. So that's a simple conversion you must know. And you must know what is the calorific value, what is the heat produced in the kilocalorie per amount of fuel is being used. That's why CV is being mentioned in the kilocalorie per kg. Plant load factor we have already explained in the yeah. Let's start with the question. This one. Next question. That is so. Please read that question carefully. The power sector of an Indian state has a coal consumption of 25 million tons annually, and the average calorific value for that coal is 1 million tons of oil generated. That is 44 billion units of electricity in the coal-based thermal power plants. The auxiliary consumptions in the thermal power plant is 3 billion unit annually. There is also an annual generation of 18 billion units of electricity from the hydro, that's having efficiency of 80%. If there is a gas-based power plant that uses 19 or 900 million tons of meter cube of natural gas that's having a calorific value of 9,300 kilocalorie per meter cube to generate 3.5 billion units of electricity, with 0.3 billion units being used for the auxiliary consumption. So here we have seen there are three systems. One is the coal-based power plant, one is the gas-based power plant, and other than is the thermal power plant. So the total sales of the unit to the customer is 49 billion units. Now we have to draw energy balance for the power sector, compute the percentage shares of the coal, oil, and the gas and hydro in terms of the primary energy consumption in the power sector. Compute the auxiliary consumption, the percentage, and the net heat rates for the coal and the gas power plants, and determine the transportation, the distribution losses, and the commercial losses in the power system. So let's solve this question. If you have any doubts, you can still ask. So now here it is given. Let me connect it. So I have to just show you the solution for this question because we don't have much time to solve this question. So and there is also some glitch that we are facing right now.
Hello, sir.
Yeah.
Sir, actually, we are facing a problem while solving the question for our assignment. As per previous question you have solved, there is a almost similar question, but there is slight change. The power plant, it is mentioned using a combined gas turbine cycle, and the primary fuel used here is methane. Then it asks the emission factor in kg of CO2 per kWh. So I am getting stuck during the conversation from methane to CO2. Can you please help it out?
Right now, I can't help you. I can help you in the next session because that's a question being asked in the quiz. So we are not supposed to give the solution for that. So that's a
Not
tricky.
solution, but you can give some hints also.
Yeah, simply hints. That's if you see in that question that we have solved, like stoichiometric ratio, we know what is the commercial equation for the power plant that uses the coal. That is coal being burnt with oxygen and generates CO2. Similarly,
Yes.
CH4, we have an equation for the CH4 plus oxygen that will generate some amount of CO2. So you have to use that equation and you can get the amount of CO2 being emitted.
Achha, I mean, that equation is the important part.
Yeah. Equation
And
part is
moreover,
important. You
on
can just
that,
get it.
as previous question, there is a percentage of carbon in the coal. It is mentioned, but there is none. in the question it is not mentioned the percentage of carbon in CH4. Is there
Yeah.
any general percentage of carbon in CH4 that I didn't get from?
Yeah. Like if you see in the stoichiometric, like CH4 is having is being as a fuel, and you can just get it. I think you can just solve it for the considering the same equation. I will see whatever that there may be some problem with the question also. So whatever the detailed part, we'll just solve it for the with the equation and all. I will solve it in the next live session. So these live sessions will be going on every week. So we'll just
Okay,
cover up
sir.
the next quiz. All I will solve all the quiz questions in the next week after the deadline. So if you have any doubt, I can just
Got it.
solve it at that time. Okay, thank you. Yeah, finally, connection is being back. Let me just solve it quickly. So now we have given coal, that is amount of 25 metric ton. We have given oil, the amount of 1 metric ton. Simultaneously, if you will add coal TPP as a 44 billion units of electricity. Now, auxiliary consumption, we generally write it as auxiliary consumption, AUX. That is 3 billion. And from the hydro, it is 18 billion units having efficiency of 0.8. From the gas, we have given 900 million meter cube of gas is being used, having a calorific value of 9300 kilocalorie per meter cube. It can generate, sorry, it will generate 3.5 billion units, and having auxiliary consumption, that is for the gas is 0.3 billion units. So here it is given in the question, coal and oil based system is same. So that's why we are just combining it. So that will be the one part. Second is the hydro. Third will be the gas plant. Now, combinedly, if you will see, combinedly, that will sales is being 49 billion units. So these are the given parts of the question. So we will see the primary, if we will solve like here, we will solve what will be the primary energy consumption, that will be for the part 1. So let me just correct it here. It is given 1 as a coal, 2 as a oil, 3 as a hydro, and 4 as a gas. So let's solve it. So don't go for that handwriting. I will just upload all the solution in the detailed version, and that will give you all the solution after the class. So I'm just solving it live, so that I just want to have that how this question is being solved, so that we give you a feeling. So for the coal, we are generating 25,000 into 10 raised to power 6 into 45 kilocalorie. That will be 1.125 into 10 raised to power 14. This is a simple unit conversion that I did it here. should be able to do this. And 1 into 10 raised to power 6 into 10 raised to power 3 into 11,000 kilocalorie. 11 into 10 raised to power 12. So that's a amount of primary energy consumption. Third is 18 into 10 raised to power 9 divided by 0.8, because here the efficiency is also given, into multiplied by 3.6 into 10 raised to power 3 into 1 by 4.18 kilocalorie. That's a conversion of kilocalorie to kilojoule. 0.938 into 10 raised to power 14. That was 12. Now, fourth one, that's the last one, gas. 900 into 10 raised to power 16 into 9,300 kilocalorie divided into 8.37 into 10 raised to power 12. So total, we are able to generate primary energy, that is 2.257 into 10 raised to power 4 kilocalorie. These all units are here that I have calculated is kilocalorie only. We have already written here, as you can see. So kilocalorie. The total would be 2.257 if you will add all this. So first of all, if you will see what is the first thing that is being asked in the question, that is what is the amount of energy, what is the share percentage of the shares of coal, hydro in the terms of primary energy consumption. So what is the thing that we can calculate from here? From that is, for the coal, that would be 1.125 into 10 raised to power 14 divided by total, that is 2.257 into 10 raised to power 14. So that comes out to be 49.8%. Similarly, if you want to calculate for the oil, that would be 11 into 10 raised to power 12 divided by 2.257 into 10 raised to power 14. That comes out to precisely 4.9%. That is for the oil. That is for the coal. Third, if you will see for the hydro, that would be 0.938 into 10 raised to power 14 divided by 2.257, that is total primary energy. That would be 41.56%. Now moving ahead to the final term, that is for the gas. That would be 8.37 into 10 raised to power 12 divided by 2.257 into 10 raised to power 14. That would be 3.7% for the gas. So that's first thing that was asked in the question we have solved. That is here. Compute the percentage shares in the coal, oil, gas, and hydro. So we have calculated this thing. Now what is the other thing that's being asked? Compute the auxiliary power consumption percentage and the net heat rates of for the coal and the gas power plants. It is being asked only for the coal and gas power plants. Let's see. So for the auxiliary consumption, we have to see what is the auxiliary consumption given in that question. So if we want to calculate for the coal first, let's go for the coal first. If you will see here, for the coal, auxiliary consumption is 300 billion units. And what is the amount of total primary energy, that is we have calculated here 2.257. So how we can generate how much of the auxiliary consumption is being in the coal power plant? So for that, you have to just calculate auxiliary consumption percentages. For that, if you will see, for the coal, auxiliary consumption was given 10 into 3 million units. So we just converted into that and converted to the units. That's a 3.6 multiplied by 10 to the power 6 and divided by 4.18 into 2.257 into 10 to the power 14. So if you will see, 4.18 was to convert the kilocalorie into the same units as that in the given in the question. And here also 10 to the power 9 is used for the millions. 3.6 is converted for, it's also a unit conversion. So if we'll multiply all these, if you can see 10 to the power 14 here, so it will just cancel out. 10 to the power 14 will cancel out, that will be a 15. So we will remain only 10 here. Finally, if you will calculate all these, so 3 into 3.6 into 10, that will be 108, and 4.18 into 2.257, that will be 9.43426. So finally, the thing that we got is 108 divided by, that is 11.4. That's finally the thing is 0.114. So that's 10.8. So 11476. So final the percentage of the auxiliary consumption that we called coal aux, that will be 11.48445. We can precisely write 45%. So that's the one thing that we have solved for the gas. For the coal. Now the similar thing we can calculate for the gas also. So gas, you will see the auxiliary consumption that we have calculated is, that is given in the 0.3 billion here. If you see 0.3 billion units. Similarly, if you will calculate for the gas, that will be 0.3 into 10 raised to power 9 into 3.6 into 10 raised to power 6 divided by 4.18, that's a unit conversion, 2.257 into 10 raised to power 14. Similarly, here also that thing will be 10. That thing will be 0. Finally, if you will multiply and calculate all these things, this will be 0.01145 precisely. Gas auxiliary consumption will be 1.145%. So that's how we will calculate the auxiliary consumption. So suppose if this type of questions are able to be solved in the quiz itself, you will given the amount of units. You just have to solve it for the auxiliary consumption. Then you must be able to solve it. Now let's move ahead for the next part. What is being asked? Heat rate. So what is heat rate? So if you go for the question, compute the auxiliary consumption and the net heat rates. So here they're asking for the heat rates for the coal and the gas power plant. So let's go calculate what is the heat rate. First one, heat rate is the heat input divided by power generation. Heat input, what is the unit of heat input? Kilocalorie divided by kilowatt hour. Let's solve it for the coal first. So heat input for the coal, it's already given the question. We have solved it for the here. If you will see 1 point, this thing I will say this thing we have solved 1.15, and for the natural gas we have calculated 8.83, 8.37. So just remember these two things, and we will solve it. What is the heat rate? The input heat energy will be 1.125 into 10 raised to power 14. If you want to convert into kilojoule, you have to multiply it by 4.18, divide by 44. What is the power generation? So the total power generation, if you will see in the question, that is 44 billion here. This thing here, 44 billion units of electricity. So there is 10 raised to power 9. Here I'm not multiplying any conversion factor because we just need it in the same units. 3.6 into 10 raised to power 3. So now that thing will be 2.97. So if you just let's not convert this into the units. So what will thing we will get? If we just simply want to have the units similar, that is kilocalorie per kilowatt hour. So that's just a division. That will things will give us 2,556.82 kilocalorie per kilowatt hour. Just verify 1.125 into 10 raised to 14 divided by 40, 44 into 10 raised to power 9. That's correct. 2,556.81. Now let's calculate quickly for the gas also. For the gas, it is 8.37 into 10 raised to power 12. We have just seen, and 3.9 into 10 raised to power 9. That will be 2391.43 kilocalorie per kilowatt hour. So what is the physical significance of the heat rate? It is the amount of heat that we are giving in the power plant to generate a 1 unit of electricity. So here you can see the comparison. To generate a 1 kilowatt hour of electricity from the coal, we need a higher heat rate as compared to the gas power plant. Now let's move ahead. What is the determine the transmission, the distribution, and the and commercial losses in the power plant? So that's very easy. Now we are just T&D losses, T&D and commercial losses. So all the things we have calculated. So we have 1.1 billion units. We have 18 billion units. We have 3.2 billion units. If you will add this, that will be around 62.2 billion units. So if you will see where it is coming from. So if you will see how much amount of electricity is being generated. So if you multiply these things with the amount of energy that we have given, you will get all these things, like what is the energy is being generated from these power plants, from these values, as you calculated for all these. And if you will see from that whole things losses, so we are able to generate 62.2 billion units. And initially we have given that sales is 49 billion units. So if you were to calculate the losses, so losses would be 49 we are able to sell. So losses will be 62.2 minus 49. That would be around precisely 13.2 billion units. So if you want to calculate the percentage, that will be 21.2% of units is being lost in the transportation and the distribution. So I hope you'll be able to grasp this question. You can go ahead with the recordings if you want to have any other doubts. And if you have any other doubts till now, I'm just able to solve it for you before moving ahead. Yeah. So that's a long question that we have solved. We have another question in the pipeline, but I think we don't able to solve it right now. Just go through in the next class. So yeah, this is the question. You can just go through it from yourself, then I will solve it into the next question. You can just have a screenshot or have a photograph. That's also a detailed question. So I will just give it to you from the what is the insight from. So these two questions typically give you the insights for the whole week. Whatever you should be able to this question is giving you the insight for the lecture 1A, 1B, and 1C. And here also we are able to calculate the chi identity and other things like installed capacity, primary energy consumptions. And other than that, so this is a big question that there are 8 questions being asked. So we have to just draw energy balance, compute the shares of different energy sources. What is the energy percent primary? So these are the same things that we have solved in this question. So you can take this as a question to be solved from yourself. If you're having any problem, I will just surely solve that question into the next class. So let me see the comments if any. Share the question for the practice. Yeah, this is the question that you can take away for the practice. And I will share some more questions if I have a question bank. And if you want typically the similar type of question that we have solved in the tutorials or like in the short question, you can go the same course in the previous year 20, 21, 23, and you can solve the similar questions and you will that will be able to help you in the quiz.
Okay. Thank you.
Any other doubt you can have that you can ask.
So when will be the next session? Is next class?
Next session, the sessions will be the same time every Tuesday.
Every Tuesday, same time, 7 to 9.
Yeah. Yeah. Let me just stop it. If you have any queries, you can ask me in that discussion forum. I will be able to answer that. Or if you have any precise queries, you can just write it down. And I will share the recordings of these lectures to the that will be uploaded in the YouTube, and all the slides that I've used. That link will be shared in that, so you can use all the slides and the questions precisely, and all the things will be available to you. Thank you. I think if you don't have any doubt, we can just bind it up for the today.
So will you share this slide like in the
we will share
NPTEL
this
forum only?
Sure.
Okay.
Okay, I think we can finish it.
Thank you, sir.
Okay, thank you.